You know, inside every single piece of tech you own, your phone, your computer, you name it, there's this kind of secret hero working behind the scenes. It's a standard called IPC-D356, and honestly, it's the reason our electronics actually work. So today, we're going to pull back the curtain and figure out what it's all about.
So picture this, a bare circuit board, right? That green slab that's basically the nervous system for your phone. It's covered in thousands of these tiny copper pathways. Now, if just one of those pathways has a break, even a microscopic one, the whole device is toast, absolutely useless. So the big question is, how on earth do you find that single, tiny error before you go and solder on hundreds of dollars worth of components? It's a huge problem.
Well, before we had a universal standard, trying to solve this was, let's just say it was a massive headache. The whole industry was stuck using a method that was slow, super clunky, and just couldn't keep up with modern electronics. This was the golden board era.
Yeah, they had this thing called the golden boards technique, and it's pretty much what it sounds like. They take one single board that they knew was perfect, the golden one, and use it as the master template. Then every single new board coming off the assembly line had to be compared against it. I mean, can you imagine? So tedious and just begging for errors to slip through.
Okay, so clearly that wasn't going to work long-term. A better way was desperately needed, and the solution came in the form of a standardized file format that finally brought some order to all that chaos: IPC-D356. The whole point was to create one single consistent language for all the testing machines out there.
So what is it exactly? The best way to think about IPC-D356 is like a universal translator. It's really just a simple text file, but what it does is brilliant. It takes all that complex design info and translates it into a language that basically any testing machine can understand. This lets it automatically and perfectly check every single connection on a board. A real game changer.
But, a lot of standards have come and gone. Why did this one stick? Why did it succeed where so many others failed? Well, according to our source, it really boils down to four key things. First, it was simple, just plain old text. It was neutral, so no one company had control over it, and it was just comprehensive enough to do the job without getting bogged down in crazy complexity.
And this right here brings us to the real genius of the format. It's incredibly clever because it manages to speak two totally different languages at the same time. It's designed to serve two very different audiences, the human engineer on one side and the robotic tester on the other. Okay, look at this. On the left, you've got the language for humans. A connection, or what engineers call a net, is described logically, something like, hey, this is the clock signal and it connects to component U2 at pin 5. Makes sense to a person, right? But then on the right, you have the language for the machine. That exact same point is described as go to physical coordinates x2300, y1200. Having both of these in one file is the magic trick. It means a robot can find a tiny fault, and the human engineer instantly knows what that fault actually means for the circuit.
All right, so what does this file actually look like in the wild? I'll be honest, at first glance, it can look a little cryptic. But the structure is surprisingly simple once you know the secret. So let's dive in and look at a real single line of this data.
Okay, here it is. One single line from a real IPC-D356 file. Yeah, it looks like a total jumble of letters and numbers, doesn't it? But believe it or not, everything we just talked about is packed into this one line. The logical name, the physical location, all of it. So let's crack this code together.
The secret, and this is key, is that this is a super old-school 80-column fixed format. Think punch cards. It means the column number where a piece of data sits is everything. Each bit of information has its own specific address on the line. And this table right here, this is our decoder RIN.
All right, let's start decoding. See that first part, 317 and click 65? That's the what and the who. 317 is a code that tells the machine, hey, this is a test record. And click 65, that's the human-friendly name for this specific electrical pathway, the clock 65 signal.
Next up, we've got the part for the repair technician, U2-5. This tells them exactly what component, U2, and which pin, pin 5, this point connects to. So if the machine finds a fault right here, there's zero guesswork for the human trying to fix it. Okay, this next chunk, D400PA00, describes the physical test point itself. It's telling the machine that it's a plated, conductive hole, what its diameter is, and whether the probe can access it from the top of the board, the bottom, or both sides. All the physical specs the machine needs.
And finally, the most important instruction for the machine, the exact X and Y coordinates. X 23,000, Y 12,000. This tells the testing probe precisely where to go on the board. And that's it. That's the whole genius of it, right there, in one line. 2 languages, human and machine, with absolutely no ambiguity.
Now, as amazing as this format is, we have to be honest. It's not perfect. In fact, its greatest strength, its simplicity, is also its biggest limitation. The author of our source material, Rich Nedball, he points out that this rigid 80-column format is, well, it's pretty ancient and could definitely be improved.
For instance, the standard kind of struggles with a lot of modern stuff, like complex pad shapes. It doesn't include any Z-axis data, which is a problem for multi-layered boards, and it could be way better at handling things like solder mask openings. Now, you could add all these things, but it would come at a cost.
And that brings us right to this key quote from the source. The author himself says, "If we try to squeeze too much out of the format, it would lose its best quality, simplicity." He's basically warning us that if you try to make it do too much, you risk destroying the very thing that made it so successful to begin with, that beautiful, effective simplicity.
And that really leaves us with a pretty powerful question to chew on. In a world that is just rushing toward more and more complexity, maybe we've forgotten that sometimes the most elegant, the most powerful, and the most enduring feature of all is just simplicity.